And here's the crazy part. A URL shortener like bit.ly handles billions of requests every month. Not million, billions.
Billions? Seriously? I knew they were popular, but that's an insane amount of traffic. What happens if they just stop working?
Chaos. Think about it. Every link shared on social media, embedded in emails, printed on flyers, a huge chunk of the internet relies on these things. If a major URL shortener goes down, it's like a digital traffic jam on a global scale.
So it's not just about inconvenience, it's about actual business impact. Imagine a marketing campaign that's suddenly dead in the water because all the short links are broken, or an e-commerce site where product links stop working.
Exactly. And it's not just about downtime. Performance matters too. If the redirect is slow, people will abandon the link. Think about how impatient users are. Every millisecond counts. We're talking about lost revenue, damaged brand reputation, the whole 9 yards.
Okay, you've convinced me. High scalability and low latency are crucial. So how do you actually build a URL shortener that can handle that kind of load? It's more than just a simple database lookup, right?
Way more. The core idea is simple. You take a long URL, generate a short unique code, and store the mapping in a database. When someone clicks the short URL, you look up the original URL and redirect them. But at scale, the devil's in the details.
All right, let's dive into those details. Where do you even start when designing something like this?
First, you need to think about the hashing algorithm. This is what generates the short code from the long URL. A simple approach is to use a counter. Increment the counter for each new URL and convert it to base 62 alphanumeric characters.
Base 62, why not just use integers?
Because base 62 gives you a much shorter string for the same number of possible values. Think about it. With 7 characters in base 62, you can represent 62 to the power of 7 different URLs. That's a lot of URLs.
Okay, that makes sense. But what about collisions? What happens if two different URLs accidentally generate the same shortcode?
That's where collision resolution comes in. The simplest approach is to check if the generated shortcode already exists in the database. If it does, generate a new one. But that can be slow, especially as the database grows.
So what's a better approach?
A more robust approach is to use a cryptographic hash function like MD5 or SHA-256. These functions generate a fixed size hash value from the URL. You can then take a portion of the hash and use it as the shortcode.
But MD5 and SHA-256 are designed for security, right? Are they really necessary for a URL shortener? Is there a performance hit?
Good question. You're right, they are designed for security, and they are computationally more expensive than a simple counter. But the advantage is that the probability of collisions is extremely low even with billions of URLs. Plus, you can truncate the hash to a smaller size to improve performance.
Okay, so we've got the hashing algorithm sorted out. What about the database? SQL versus NoSQL. What's the right choice here?
That's a big decision. SQL databases like MySQL or PostgreSQL are great for relational data and ACID properties. You get strong consistency and reliability, but they can struggle to scale horizontally to handle billions of requests.
So NoSQL is the answer then. Something like Cassandra or DynamoDB?
Not so fast. NoSQL databases are designed for high scalability and availability. They can handle massive amounts of data and traffic, but they often sacrifice consistency for performance. You might end up with stale data or inconsistent redirects.
So it's a trade-off, consistency versus scalability. Which one is more important for a URL shortener?
For URL shortener, availability is usually more important than strict consistency. It's better to serve a slightly outdated redirect than to have the entire service go down. So a NoSQL database like Cassandra or DynamoDB is often a good choice. Think about how Amazon uses DynamoDB for many of its high-traffic services.
But wait, doesn't eventual consistency mean that sometimes the short URL won't work immediately after it's created?
Yes, that's a risk, but you can mitigate it by using techniques like read repair and hinted handoff. These techniques ensure that data is eventually consistent across all nodes in the cluster. Plus, the delay is usually very short, on the order of milliseconds.
Okay, so we've got the hashing algorithm and the database. What's the third key component of a distributed URL shortener?
Caching. Caching is absolutely essential for performance. You want to minimize the number of requests that actually hit the database.
Makes sense. Where would you put the cache?
You can use a distributed cache like Redis or Memcached. These are in-memory data stores that can provide extremely fast lookups. You can cache the mapping between the shortcode and the original URL.
So when someone clicks on a short URL, you first check the cache. If the mapping is there, you return the original URL immediately. If not, you query the database, store the mapping in the cache, and then return the original URL.
Exactly. And you can use different caching strategies, like LRU or least recently used, to evict less popular URLs from the cache. Think about how Netflix uses caching extensively to deliver video content to millions of users.
Okay, this is starting to come together, but here's where it gets interesting. What about custom short URLs? Like if I want my short URL to be example.com/mycoollink instead of some random string.
Custom short URLs. That's where things get a bit more complex, because you can't just generate a random code. You need to check if the custom URL is already taken.
So you need to add a unique constraint to the database for the custom URL field.
Exactly. And you need to handle the case where someone tries to create a custom URL that's already taken. You can either return an error or suggest a similar URL. This is where you start to see the limitations of a purely NoSQL approach. The need for strong consistency around unique custom URLs often pushes teams back towards SQL for at least part of the system.
Wait, so you might actually need both SQL and NoSQL in a production URL shortener?
Precisely. You could use NoSQL for the bulk of the redirects, which are mostly read-heavy and can tolerate eventual consistency. But for custom URLs, where uniqueness is paramount, you might use a SQL database to enforce that constraint. It's about choosing the right tool for the job.
Okay, mind blown a little. So what's the biggest mistake engineers make when designing a URL shortener at scale?
They underestimate the importance of monitoring and analytics. It's not enough to just build the system and deploy it. You need to constantly monitor its performance and identify bottlenecks.
What kind of metrics should you be tracking?
Everything. Request latency, error rates, cache hit ratios, database query times, the number of new URLs created per day, geographic distribution of requests. The more data you have, the better you can optimize the system. Think about how Uber uses real-time analytics to optimize its routing and pricing algorithms.
So what should a software engineer do differently after listening to this? Give me 3 actionable takeaways.
First, don't underestimate the complexity of building a URL shortener at scale. It's not just a simple side project. It's a distributed system with many moving parts.
Okay, so treat it like a real production system, not a toy project.
Second, choose the right database for the job. Consider the trade-offs between consistency and scalability. Don't be afraid to use both SQL and NoSQL if it makes sense. It's not an either-or situation.
So be pragmatic and choose the right tool for each specific requirement.
And third, invest in monitoring and analytics from day one. You can't optimize what you can't measure. Think of it as building a cockpit for your system so you can see all the key metrics at a glance.
All right, that's a solid plan. So if I had to sum it up in one sentence,
building a URL shortener that can handle 100 billion requests is like building a bridge that can withstand a hurricane. It requires careful planning, robust materials, and constant vigilance.